In this example, we're going to deal with our dynamics of a rotating rod. So let's suppose that a rod of uniform mass M is attached to a wall by a hinge. So we're holding our rod along the x-axis. The rod has mass M and is attached to the hinge, which is attached to a wall. So the hinge acts as an axis of rotation. So if we let go of the rod will rotate about the hinge, which serves as the axis of rotation. So at the moment we let go of our rod, it begins rotating in the clockwise direction. Now at that exact moment when we let go of the rod, we want to calculate two things: the angular acceleration of the rod as well as the linear tangential acceleration at the tip of our rod. So let's begin with our angular acceleration. So let's make the assumption that the entire length of our rod is given by the capital letter L. Now recall what the moment of inertia of a uniformly massed rod is. So if our distance of the rod is L and the mass is M, well then the moment of inertia is equal to 1/3 multiplied by the mass multiplied by the square of our distance L squared. We're going to need to use this in just a moment. Recall that our analogous equation for Newton's second law of motion for angular motion is given by the following formula. Our net torque acting on the object is equal to our moment of inertia of the object multiplied by the object's angular acceleration, which is given by alpha. So what exactly is the force acting on our object on the rod that's creating that motion, that's creating that rotational motion? So we need to find what the force is that creates our torque. The only force acting on our rod when we let go of the rod is the force of gravity. And the force of gravity acts at the center of gravity. And because our object has a relatively small mass, we make the assumption that the center of gravity is the same point as the center of mass, right in the middle of our object. So if the entire length of our object is L, that means the position from the hinge to the center of gravity is L divided by 2. So knowing this information, let's rearrange this equation and solve for our alpha, for our angular acceleration. So angular acceleration, which is what we're looking for, is equal to the torque divided by the moment of inertia. So the moment of inertia is given by this formula. So we substitute this into this I, and then we substitute M times G times our lever arm L divided by 2. So F is simply the force of gravity, and F multiplied by the lever arm gives us our torque. So F is M times G. Notice that M appear at the top and the bottom, so we cancel them out. Now we have one L at the top and two L's, or L squared, at the bottom. So we cancel out one of the L's, and we're left with our angular acceleration of the object is equal to 3 times G divided by 2L. So notice, as the rod begins to rotate its lever arm, the quantity of L begins to change. And that means as our object is rotating, even though the force of gravity is constant, the angular acceleration of the object is not constant. It changes. Now let's look at part 2. Let's find the tangential acceleration of the object at the tip. So once again, at the moment that we let go of our rod, the rod begins to rotate, and at that moment, our tangential acceleration points in this direction, in the same direction as the force of gravity. Now, the formula of our tangential acceleration that relates our lever arm, our distance, and our angular acceleration is given by this equation. A tangential is equal to alpha multiplied by r. So in this case, our alpha is simply the alpha that we found in part 1. And now r is simply the entire length of our rod. So it's from the hinge to the point where our object is experiencing tangential acceleration. So we have 3g divided by 2l multiplied by l. Notice the l's cancel, and we're left with 3 divided by 2, or 1.5g. Now notice a very interesting point. The tip of the rod accelerates faster, 1.5 times faster than the gravitational acceleration. And what that means, if I take an object, let's say if I take this marker and place this marker on top of my rod, and I let go of the rod and I let go of the marker at the same exact time, the marker will be left at the top because this rod will accelerate 1.5 times faster than our object on the tip of that rod.